Okay, we have here another problem to add to our limits playlist. We have the limit as x approaches infinity of 2x plus 3x squared plus e to the minus x over 2x squared plus cosine x. Okay, to get started with this, I'm just going to try to evaluate it and see what's happening at infinity. So just kind of plugging in as much as we can plug in infinity. 2 to the x plus 3x squared, that's all going to infinity. But then for e to the minus x, we can look at that as 1 over e to the x. And so when x is going to infinity, this is going to 0. But still in the numerator, we're going to infinity. And then the denominator, same thing here, 2x squared is going to infinity. Cosine x is kind of bouncing back and forth between 1 minus 1, but it doesn't matter because this is going to infinity. And so what we have here is an indeterminate form, and what I'll do now is try to pronounce L'Hopital's rule. Okay, over here to the right, we've got our definition of L'Hopital's rule, which says when we have one of these indeterminate forms, 0 over 0, or an infinity over infinity case like we have in our problem, then we can use this definition for a rational expression that instead of taking the limit of that expression, we can take the limit of the derivative of the numerator over the derivative of the denominator. So using this on our problem here, we're still going to be taking the limit as x goes to infinity, but we just need to take some derivatives. So first, the derivative of the numerator is going to give me 2 plus 6x minus e minus x. And then taking the derivative here, this is going to become just 4x. Derivative of cosine x is going to be minus sine x. But then evaluating it again, at 6x is going to infinity, so the other terms aren't really going to matter. So the numerator is going to infinity. And again, 4x is going to infinity. Sine is between 0 and 1, that's not going to matter. So again, we have an infinity over infinity case. But then what we can do is just use L'Hopital's rule one more time. So we'll again be taking the limit as x approaches infinity. We'll take our derivatives. Derivative of 2 is 0. Derivative here is going to be 6 plus e minus x. Derivative here is going to give me 4 minus cosine x. Then evaluating this limit, when we plug infinity in for e to the minus x, again, this piece is going to 0. So in the numerator, we end up with 6. Then plugging infinity in here, well, we're going to have 4. But then taking the limit at infinity of cosine x, well, it doesn't converge to any value. It's just bouncing back and forth from 1 to minus 1. So this limit actually does not exist. But the trouble here is we can't go and use L'Hopital's rule again because we don't have, it's not one of these cases. It's not 0 over 0 and it's not infinity over infinity. So I would just say this isn't a good case for L'Hopital's rule and we should just back this out and try it a different way. Okay, so what I want to try here instead is just look at our polynomial part, like look at 2x squared here, 2x plus 3x squared, and look at the highest degree term, which in both cases is the square term. And then let's just try to reduce that. What I'll do is multiply by 1 over x squared in the numerator and denominator. And so doing that, let's just take a look at what we have. So first, 2x times 1 over x squared, this is going to give me 2 over x. Then here, this is just going to be a 3. And then here, we're going to have e minus x. But then what I'll do, I'll put it all in the denominator. I'll write it like x squared e to the x, just to make it clear. Then here, this is going to just become 2. And then this is going to be cosine x over x squared. But now at this point, by doing it that way, I think we can evaluate each piece of this. So first, for 2 over x, when x is going to infinity, this here is going to 0. We're going to have this 3 here. Now here, again, this one's clearly going to 0 when x is infinity. So in the numerator, we're just going to have a 3. Then here, we'll just have 2. But now notice the problem we had before with cosine is fine now, because if we have cosine going between minus 1 and 1, but we have x squared going to infinity, well, this piece is clearly going to 0. And so our denominator just becomes 2. And so the final solution for this is just 3 halves. Okay, I actually forgot to mention at the beginning of the video, I actually got this problem from UNSW cpms 2008. This was problem 5. When I went back in history, I found they had other problems that weren't just integrals. That's it for today. Thanks everyone for watching. Have a good day.